We also celebrate his enduring influence as a defender of learning and equality. The Kambule Doctoral Award embodies his spirit, recognizing doctoral research of exceptional depth, significance, and potential to impact both theory and practice, especially when it comes to advancing African scholarship within machine learning and artificial intelligence. Before I continue, I'd like to take a moment to sincerely thank the 43 reviewers from across Africa who have worked tirelessly behind the scenes. Despite their busy schedules, they committed themselves to ensuring that every application received the attention it deserved. Can we please take a moment to give them a round of applause? Thank you. Today, we are here to recognize the remarkable achievements of doctoral candidates whose research exemplifies excellence, innovation, and societal impact. It is my pleasure to announce the winners of the 2025 Kambule Doctoral Award. First place goes to Lexy Andati for outstanding research in radio astronomy, combining technical innovation and impactful analysis to advance African scientific knowledge. The runner-up is Geraud Nangue Tasse for pioneering work in reinforcement learning, bridging theory and practice to elevate African AI research and applications. Congratulations to Lexy and Geraud. Your dedication, ingenuity, and commitment to excellence inspires us all. They are going to come up to briefly tell us about their work. So now I'd like to invite Lexy to come and tell us about her work. Thank you.
My name is Lexy Andati. I am a postdoctoral fellow at the Center for Radio Astronomy Techniques and Technologies at Rhodes University in South Africa. My research is in the field of radio astronomy and astrophysics. I wrote a PhD thesis that is both scientific and spanning both scientific and computational sciences. And the thesis title was Meerkat Polarimetric Observations of Picture A, which was supervised by Dr. Lerato Beidu and Professor Oleg Smirnov. Don't worry about the terms on the title, we'll get through them shortly. So this is a slide I'm very passionate about. Astronomy is not astrology. No, we don't read horoscopes, and we definitely cannot tell you whether you're gonna meet the love of your life in the next 3 to 5 business days. We don't do that. We study celestial bodies, so your planets, your stars, galaxies, and typically, when you talk about astronomy, we think about astronomy in the visible frequency. But it turns out celestial objects give off other kinds of electromagnetic waves all across the electromagnetic spectrum, which I show at the bottom there. And the field in which I work, we deal with waves from the radio spectrum. So particularly, I'm concerned with galaxies. A galaxy is a collection of stars, dust planets that are gravitationally bound together. So when I talk about radio galaxies, I'm just talking about a galaxy that is more visible or very visible in the radio frequency. So how do we do radio astronomy? We use radio telescope. This one looks like your typical entertainment satellite dishes, but on a much larger scale. And the idea is that we are collecting signals from galaxies that are very far away, so we'd like to collect them as much as possible on as large surface as possible, but it's physically not possible to build very large dishes. So we take a bunch of smaller dishes. They collect the signals together. We combine the signals taken from those small dishes to form astronomical images. So basically, multiple dishes simulating one very large telescope. For my PhD, I used data from the Meerkat telescope. This is based in South Africa. It has 64 dishes. And Meerkat is a precursor telescope. And this means it's just preparing the way for a much larger telescope, the Square Kilometer Array. I'm sure some of you have heard of it. And what we do with Meerkat is we are preparing for the data that is to come with the SKA. We prepare tools on how to process that data. The Square Kilometer Array is a very ambitious project. It aims to have an effective collecting area of 1 square kilometer. That's quite big. Okay, so what does data processing for radio astronomy look like? We get our observations from the galaxy, from the observatory, and then we do what is called calibration. This is cleaning out prior known or unknown effects. And this is a very repetitive and begrudging process. It takes months to get calibration right. And after we think the calibration is good enough, we end up with astronomical images, and this is where the science begins. So we get astronomical images, we look at them, what features can we see in our galaxies, what science can we extract out of that. And after the scientific analysis, we also build tools to help scientists achieve their scientific goals. So the calibration, imaging, scientific analysis, and building tools is the span of my thesis, whose QR code is there. You can feel free to scan it if you want to read the thesis or more in depth about my work. So in the title, I talked about Picture A. Picture A is the galaxy I chose to focus on. This is a galaxy located in the southern hemisphere, and it's quite a large galaxy. What I show here is the image of Picture A. It's a full-scale astronomical image, and this is the image that we got from our data. The technical part about imaging this galaxy was that western hotspot is very bright, and it outshines the rest of the galaxy because the rest of the galaxy is very faint. So we need to be able to see both the bright and the faint parts of the galaxy. So we were able to do that, and we were able to come up with this image with a high dynamic range, so we are able to see all parts of the galaxy and do our science on it. This galaxy is 1.3 million light years wide. That means if you're traveling at the speed of light from one end to another, it will take you 1.3 million years to get through it. So it's quite large. It's also very far from us. And so if we can see such galaxies with so much detail from Earth, you can imagine its size. For context, imagine a plane on the ground and a plane in the sky. It's barely a dot there, so if you can see this much, then it's quite a huge galaxy. Okay, so in my title, again, there was polarimetry. And polarimetry is just the study of magnetic fields. So the goal of this work was to study the magnetic fields of that galaxy Picture A, and how we do that is using multi-frequency radio observation. So we take our observation, divide it into chunks. This gives us multiple frequencies, and we're able to map out the kind of the signal, how the signal changes on its way to us as it passes through a magnetic field. This is the main equation we use. The P lambda squared is in the observation space. That's what we observe. And the F phi is in the magnetic space. So we move from P lambda squared to F to get to our magnetic field. Because we cannot see magnetic fields directly, we only see their effect on the electromagnetic wave, which is what I show here. As a wave is coming from the galaxy, if it passes through a magnetic field, then it kind of changes. That's the effect we use as a diagnostic for our magnetic field. How much data are we dealing with? Well, Meerkat is able to produce a lot of data. Our particular data was 4 terabytes large, the raw data. And after processing and imaging, we ended up with 4K by 4K images. Each was 65 MB. Since we're doing multi-frequency polarimetry, we needed multiple images in multiple channels, so we ended up with 80 images. But For radio polarimetry, the more channels, the better. So we do have cases where we end up with much more number of images, and this requires proper processing. How do we fit all this in memory? Well, one option is to just have a lot of RAM. The other one is to do chunk data processing, which is kind of what we implemented in some of our work. So now I'm going to show just part of the work I did, because the rest is very scientific and technical. I'm going to show you what is applicable to this conference. The first two we did was called SMOPs. We realized that during our modeling and calibration, it's better to have multiple channel images. It gives us better calibration. But to do that, to generate model images in so many channels is computationally expensive, and it is time consuming. So we decided, why not generate those images at a coarse frequency cadence, and then interpolate them onto a finer frequency cadence for our calibration. So that's what this tool does. It's Python-based, and we use Dask for chunked process, the out-of-core data processing, so that we manage our memory and not be greedy in a shared resource compute environment. The next thing was, okay, we're able to process our data. We want to see data from lines of sight of our galaxy. A line of sight is, imagine you're just looking at a galaxy and you're looking at one point exactly. So along a straight line, the signal that's coming to you, that's what we call a line of sight. And we wanted to show the spectra of various line of sight across that galaxy. What I show in this plot here is an example. The left side is the p lambda squared, and the right side is the f phi from the equation that I showed previously. And what such plots tell us is, especially the right-hand one, it tells us the path that our signal is going through before getting to us. How many magnetized screen is it passing through? When we see one peak, we know it's probably one. If you see multiple, there's probably a lot happening there. So these are very useful diagnostic plots, and we did a tool to generate them all across our galaxy. Okay, after generating spectra across the galaxy, now we decided we want to share this work to the larger scientific community for criticism, for the purpose of data sharing. So we built another tool called Polavis, and this is web-based on Linux, Apache JS9, and Node.js. And this just allows people to go to the website and click on the various lines of sight. The green circles are the lines of sight. And when you click on them, you're able to see the spectra for that associated with that line of sight and make your own conclusions, and this is done for transparency and sharing data information. Okay, and then finally, a simple pipeline that was bash-based to do all the post-processing work from the astronomical images up to our diagnostic radiospectral polarimetric plots. This was just done because it was a lot during the experimentation. It was very repetitive, and doing everything step by step was a lot of work. So this was automation in that sense. So why is this work important? Well, magnetic fields, they play a very, very important role in the evolution of galaxies, and they're still not well understood. It's a very technical area of radio astronomy. So a lot of people shy away from it, run away from it, don't even look at it. This is why it's important. And it requires careful data processing for a lot of data. I've just talked about 4 terabytes of data. This is not a typical observation. Some observations run over days, and that's a really large amount of data, so it requires proper processing. And there's so much data, but not enough well-documented, well-built tools. So this is essentially my work, to try and build well-built tools, well-documented tools to do radio spectral polarimetry within radio astronomy field. And I consider this one of Africa's contribution to international astronomy and science. So for my future plans, I would like to specifically do some image classification for my spectra. As I said, some spectra show a single peak, others show multiple. We can get thousands of lines of sight. It would be nice if there was an easy way to categorize those spectra and be able to do our science using the output from that. Okay, as I end this presentation, I just want to thank DLI for recognizing our work and allowing me to be here this week. I also want to thank the people without whom this work would not have been possible, my supervisors, my friends, families, and colleagues who supported me through my journey, and some of them are seated here or somewhere in this conference. Such awards give me the courage to continue my research without fear. I want to dedicate this award to all the African women, a lot of who are represented here, and those who support them in their journey. I hope my winning this award will encourage other young women and girls to pursue science. I also hope that they will see that it is not only possible to tackle scientific challenges, but it is also possible to do it excellently. Asante sana.
Thank you so much, Lexy. It's very inspiring to see African women reach astronomical heights within science. Next, I would like to call our runner-up, Geraud, to speak about his groundbreaking work in reinforcement learning.
Hi, everyone. I am Geraud Nangue Tasse. I am a fellow of the Mind Institute at this university. So my research is focused on reinforcement learning. I've kind of always been interested in intelligence, how intelligence arises in human beings, how human beings are able to be so general. And ultimately, I can feel that as we kind of understand better intelligence, ultimately we kind of hope to have multiple purpose robots that are as intelligent as human beings, at least at a cognitive level, and are able to do the diverse variety of tasks that human beings are able to do with similar level of generality. So that was kind of like the core motivation for my research. So actually before that, I kind of forgot to kind of express my gratitude towards this, for receiving this award. It's kind of like truly a privilege, kind of like thinking way back when I was in high school and kind of like imagining of seeing doctors and researchers kind of like producing incredible advances in science and kind of thinking that I kind of reached this point in my career where I actually have like a doctorate. It's kind of like surreal in a sense. And it's also kind of like a privilege that I'm receiving this Kambule Award, given that the lab where I was kind of like working on this research thesis is also called like the Kambule Science Building. So it's kind of like really fulfilling. So I've always been interested in kind of intelligence, and I think for most of us, we kind of really take inspiration from kind of like seeing how babies are born knowing pretty much nothing and kind of like learning their various skills and abilities throughout their lifetime by kind of like interacting with their environment and kind of learning like what motor controls, like what skills enables them to achieve the various goals they want to achieve in their environment. So ultimately, we want multi-purpose robots, right? We want agents, for example, robots, that can solve multiple complex tasks in an environment such as the real world. But fundamentally, I kind of try to look at intelligence in a more general sense that is not specific to a particular application, right? So it could be robotics, it could be kind of like video games, it could be whichever domain is of interest to one person. I would like agents to be as sample efficient and as general as possible in such environments, because I kind of like really believe that that is the level of generality that we human beings have. So consider, for example, you have a robot, maybe sometime in the future, a domestic robot, and it is in an office domain. And you kind of maybe want it to, I don't know, deliver mail to an office until there is no mail left, and deliver coffee to the office while there are no more people in the office, and finally kind of maybe patrol the office area, maybe for security, right? This is just one example of an extremely long task that you may want a multi-purpose robot to be able to do in the future. And it needs to be able to do any such task that you ask it. So like what type of knowledge representation should an agent learn to be able to be so general? what type of skills should an agent kind of like represent or try to pursue to be able to be so general. And then also, how do you instruct agents to be able to solve such tasks, right? So ultimately, when I was working on my thesis, I kind of categorized three main, I think, desiderata that we want from our agents, especially also in this age where AI is kind of like being extremely popular and kind of like advancing so fast. There's also issues about safety, about instructability, and so on. Kind of like really care about those properties, right? As one day in the future, these agents are going to have very important roles to play in our daily lives. So the first property is flexibility. We want agents to be able to solve a variety of tasks in their environment. The second property is instructability. We want agents to be able to be instructable. You want to be able to have a robot, and you can tell it that you want it to do a given task, and it understands exactly what task you want it to solve, right? And I hope these are kind of like intuitive properties, and we're going to see very soon that current AI systems do not really have any of these intuitive desiderata that we would ideally like them to have. And finally, reliability, right? We want to have some guarantees that these behaviors that our agents are executing in an environment actually satisfies the instructions we gave them. If we do not have such guarantees, then it is kind of really unsettling to have such agents kind of like be acting in the real world and help us with daily lives. Okay, so I hope that is good enough of a motivation. So the three main challenges for this. The first one is, and I'm sure anyone working in reinforcement learning or machine learning here knows, is learning is extremely slow, right? We need like billions of samples, be it in supervision or even way worse in machine learning, to learn. We need billions of samples to kind of like learn any skill we want to learn, right? The second problem is defining tasks is extremely hard. The second problem is defining tasks is extremely hard, right? In reinforcement learning, we mainly define tasks based on reward functions, but as maybe some of you have kind of like come across, reward functions kind of like are really hard to define, and they may lead to undesired behaviors if you're not really careful on how you define them. And finally, solving tasks reliably is extremely hard, right? And unfortunately, the animations are not showing, but that is kind of like the high-level kind of like overview. So we are all familiar with the reinforcement learning loop, right? You have an agent in an environment taking action and receiving feedback from the environment. So the first key result I obtained from my thesis was, how do you formally define tasks for agents to be able to understand the given task instructions and convert them into a reward function, which is what reinforcement learning maximizes. The second key result which I obtained is that if you do not do this in a principled way, you get undesirable behaviors. Right? So imagine you have a domain like this. On the top there, I'm showing a reward function and value function, which corresponds to the skill the agent has learned. And then if you want the agent to, let's say, pack all red objects, and that is the skill you have learned, and then you want to do the opposite of that, if you're not really careful on how you define your compositions, then it leads to extremely unexpected behaviors. Like imagine this, not in this simple domain, but in the factory or in the real world. You do not want such unexpected behaviors from your agents. But if you use the composition approach, which we kind of like developed in our thesis, you're able to provably obtain reward functions for the behaviors you want agents to have. The second key observation was that these rewards really depend on the boundaries of your reward function. But that's a bit too technical. If anyone's interested in that, you can speak to me later on. The third key property that we kind of like, or the third key part of our framework was that agents need to learn goal-based value functions. Right? Learning regular value functions in reinforcement learning are not sufficient for generalization. And so we introduced a simple modification to a familiar reward reinforcement learning loop to enable agents to learn goal-based behaviors. And I'm going to skip through this very quickly, but the high-level note is we achieved this like learning how to achieve any goal in the environment without any additional assumptions, which is made throughout the literature, all right? We do not assume intrinsic rewards. We do not assume ideas about motivation, any such thing. The agent learns how to achieve any goal in the environment solely from reward maximization. And this is an illustration of you can move from reward function to a world value function to actually solving the task that was given and the robot actually executing that task, right? We then show that you can compose your skills similarly as you are composing your reward functions, and this leads to provable generalization. This is the reliability that we wanted to show. Right? So we have flexibility in the form of we can compose our value functions to obtain new skills. We have reliability in the form that we have provable guarantees on the skills we obtain, and we have instructability in the sense that these reward functions, which are usually arbitrary, now you can just instruct agents using natural language or any formal language, and the agent can automatically translate that into a reward function which corresponds to the task you meant. I have some guarantees on that. So I hope at the high level, those those make sense, and those are the three main results from our thesis. But if anyone has any questions relating to the details, feel free to come chat to me. Thank you.
Thank you so much, Geraud. Thank you to everyone who's here today for being part of this vibrant community, being committed to excellence and equality and impactful research. Let us continue to support and uplift the next generation of African scholars.